Got it. So basically, a matrix is a rectangular array of elements. Uh, the size is m cross n, where m is the number of rows in a matrix, n is number of columns in a matrix, and aij is the element at the intersection of ith row and jth column. Okay. When number of rows and number of columns are equal, it's called a square matrix. Now, given a matrix is transpose. So transpose of a matrix is obtained by interchanging rows and columns. So instead of writing these stocks like this, suppose so I had these stocks as different rows. So instead of that, if I had my stocks as different columns, then what I'll get is another matrix. So if I take form 1, form 2, form 3, form 4 as columns, and the values of stocks on Jan 1, Jan 2, and so on till December 31st, then I will have this 365 cross 4 matrix. Okay. Now the difference between this matrix and the previous matrix is that an entry here, form 1 value, or rather an entry here. Let's say this entry here. Form 1 stock value on Jan 2. So this was position A12. Now this position will now be here. Right, so Jan 1, Jan 2. So firm 1 stock value on 2nd of January will now be here, which is basically A21. So the position which was earlier, the number which was earlier in position A12 will now be in position A21. All right, so a transpose is just obtained by interchanging rows and columns. What happens is that Aij in matrix A becomes AJI in A transpose. So this number which was at position 2, 1 will become position 1, 2. Right? So this is what will happen. This number will become this number. This position was earlier 3, 2. Now this position becomes 2, 3. Okay. This entire column now becomes this entire row in that order. So rows become columns and vice versa. So this is what happens when you take the transpose of a matrix. Now, a lot of times you will see textbooks writing vectors in this format. So what are vectors? Vector is basically some n-dimensional some n-dimensional vector you have. So it has n numbers, each number corresponding to a different dimension. All right, so suppose you have x, y, z. So you are working in 3 dimensions. So x, y, z equals to 3, 4, 7. What does this mean? It means x is equals to 3, y is equals to 4, z is equals to 7. So why are we interested in vectors? So suppose we are dealing in 3 goods, x, y, and z. So the bundle x, y, z will be represented as a vector. Now, ideally, vectors in linear algebra are not going to be written horizontally. They need to be written vertically. What they are called is a column vector. So generally, vectors are going to be written vertically. So what happens is when I write vectors vertically, it takes up a lot of space, right? Because we are not living in Japan. If we were living in Japan, then we'll write vertically. But we don't. We use English language. English language is written horizontally. So when you want to write something vertically, it takes up a lot of space. So a lot of unused space. So just to save space, what happens is a lot of times vectors are represented as V transpose. Okay. So when you read some textbook which in which you see vectors being represented as A transpose or X transpose. It's just to save some space. That's all they are doing. So X transpose equals to, or V transpose equals to 1, 2, 3 implies that V equals to 1, 2, 3. So just to save up this space, because initially these used to be printed, right? So you would worry about how much pages you are using. Now everybody is using PDF, so nobody cares. In any case, old textbooks still come in print and they still use this lingo. So when you see vectors represented as VT, it's basically just that they are writing it in transpose format to save up some space. Also, a matrix is called symmetric if A equals to A transpose. Okay, so a matrix is symmetric. A matrix A is symmetric if and only if A equals to A transpose. Okay. So this automatically leads to a conclusion that if A is symmetric, then A must be a square matrix. Why do I call this conclusion? So if A is symmetric, then A equals to A transpose. Now, the dimension of A was suppose M cross N, then dimension of A transpose would become N cross M, right? Because rows become columns. So now I'm saying these two matrices are same. So it should imply that their dimensions must be same. So M should be equal to N and N should be equal to N. Okay, what does it mean for two matrices to be same? Matrices same means that each element in this matrix is same as each element in this matrix. So if A matrix is 1, 2, 3, 4, all right, and B matrix is also 1, 2, 3, 4, only then I say that they are equal. Equality means they are same element by element. Okay, so it needs to be same element by element.
Before jumping onto the formal definition of
Okay, so there needs to be equality element by element. Only then we say that the matrices are equal. All right, now the most important role of matrices in math is going to be solving linear equations. So let's look at how we use matrices to solve linear equations. So let's start with some simple equations. 2x minus y equals to 1 and x plus y equals to 5. So 2x minus y equals to 1 and x plus y equals to 5. So if I were to solve this system of equation, it's very easy. I'll add them up. I'll get 3x equals to 6, which implies x equal to 2. I'll take this x equals to 2, substitute it back in any of the equations. So I'll get y equals to 3. So this is the solution. I've done it. Okay. Now, this is very easy to do because it's just two variables. Now, obviously, if I were to do x1 to x10 in 10 variables, you would have 10 equations in 10 variables. It would be difficult to handle. So we are going to look at the basics in two variable because it's easy to understand in two variable, but the basics which we learn in two variable can even be applicable in 10 variable cases. So first of all, okay, this is a system of equation. This is my equation number 1. This is equation number 2. Now, what does this mean? Okay, so there are two angles here. One is the coordinate geometry. So in terms of coordinate geometry, both these equations represent lines. So this is line 1 and this is line 2. So if I were to draw these lines on the coordinate axis, then line 1 would be when y is 0, x is equal to half. And when x is 0, y is equals to -1. So it would be this line. And line 2 is x plus y equals to 5. So it's going to be just 5 here and 5 here. I'm going to connect these points. It's going to look like this. The intersection point of these two line segments is 2, comma. So this is the coordinate geometry interpretation of this system of equations. Okay, so suppose I have a more complicated version of this thing. For 3 variable, let's say I'm taking variables u, v, and w. So I have these 3 equations. So what these 3 equations imply is that now this is line 1, this is line 2, and this is line 3. So I am looking at the intersection of these 3 lines. Okay. How to solve them is going to be second step. First, we are going to look at what does it mean when I'm solving a system of equations. What am I actually doing? So the coordinate geometry thing is you have a bunch of lines which you are trying to find the intersection point. So now you can extrapolate this to beyond 3 dimensions also. So if you have, let's say, 10 different equations in 10 dimensions, then each of these equations represents a line in 10 dimensions. Now, obviously, imagining a line in 10 dimensions is not possible because see, our world is restricted to 3 dimensions. We cannot go beyond 3 dimensions in our imagination. But mathematically, if you had equations like, let's say, alpha 1 x1 plus alpha 2 x2 and so on till alpha 10 x10 equals to 0. This was line 1, let's say. Beta 1 x1 plus beta 2 x2 and so on till beta 10 x10. This was, let's say, line 2 and so on. So you had your 10 lines. So each of these equation represents a line in 10 dimensions. Okay, so you have 10 different lines in 10 dimensions and you are trying to find how they intersect. So that's the visualization part for multivariables, multi-dimensional things, more than 2 dimensional basically. Now, another visualization is basically you start looking at these things as column vectors. So stop looking at this as, yeah, stop looking at these as lines and write them in this format. Okay. So when I write it in this format, the first equation is 2x minus 1y equals to 1. 2x minus y equals to 1. So that's the first line. The second equation becomes this one, which is 1 times x plus 1 times y equals to 5, which is basically x plus y equals to 5. Right? So these are your 2 equations. So in this, so these 2 formulations are same, but why do I write it like this? So the reason I'm writing it like this is I'm saying that this vector v1, which is 2 1, and there's this vector v2, which is -1 1, and I'm taking some combination x times v1 plus y times v2. It gives me the point 1 comma 5. So look at this figure. So this is my vector 2 1. This is my vector 2 1, and This thing is my vector -1. So I want to use some combination of these two vectors in order to reach this point 1, 5. So what should be the combination I use? When I say x times 2, 1, this x could be some multiple with which I multiply my variable 2, 1. So when x is, let's say, 2, so what I'm saying is that extend this vector 2 times. So make twice of this vector. So this vector, when it goes 2 times, it becomes 4, 2. Right? So that's what I'm saying. So I don't know what this multiple should be, but there should be some multiple of 2, 1 and some multiple of -1, 1, which should yield me to the point 1, 5. That is the aim. So this x and y are some multiples of vectors 2, 1 and -1, 1, which should help me reach the point 1, 5. Yeah. So these are different visualizations. So coming back to my 3-dimension thing, how do I write it in vector format? So u times the first vector is 2, 4, -2, right? The second vector would be 1, 6, 7. Sorry, some error. Either there should be a negative here or there should be a positive here. Anyway, we'll come back to that. And finally, 1, 0, 2. And the last thing is these numbers, they come back here as it is. Okay. Change this. Okay. All right. So this is how you can switch from one representation to another. Now, solving it is the second step. The first step is knowing that what are the different scenarios we can end up in. So when you talk about intersection of lines, so suppose we are looking for the intersection of 3 lines. So coming back to this sort of representation, we have 3 lines in 3 dimensions and we are trying to find the intersection of these 3 lines. So we could have a situation like this where there are 2 lines which are parallel to each other. The third line is intersecting both of them. So there is no common intersection point. So what I'm basically trying to do is I'm trying to find the intersection of 3 lines in 3 dimensions. So it is possible that these 3 lines have no intersection, which implies there is no solution. This also corresponds to no solution. Okay. This case also corresponds to no solution. And this is the case where the lines intersect along a complete line. So to imagine this, think of yeah, let me try to draw this in the page. So suppose this is my x and y axis and this is my z axis, right? So wait, this is, let's say, my x, y and z axis, right? So you can imagine okay, this imagination might not work. So rather, let me give you an imagination for, suppose this is the corner of a room. Okay, so this is your room, this is your wall 1, this is your floor, and this is your wall 2. So there's this one line which is hmm, Okay, this is probably something which will give you difference. So what I'm calling a line, you should think of this more as a plane. Okay, in linear algebra terms, I'm calling it as a line, but you can think of it as a plane actually in 3 dimensions. So, so this plane is basically this entire surface, right? Like your tabletop, your laptop. So these are all planes. So instead of thinking of them as lines, think of them more as planes in 3 dimension. So that would give some better intuition. So here I have a situation of two parallel planes and one of the planes intersecting them. So imagine this is the floor and then there's a table here on which you are studying. So this table and your floor are parallel to each other, right? The table and the floor are parallel to each other. So, so in this case, if you imagine the three planes as the wall, as wall one, the floor and this table, then you are going to have no intersection, right? I should probably have distinguished this case of line and plane before. Mm. Anyway, these are actually planes. These equations are going to represent planes. I'll tell you what equations are going to represent lines. I'll come back to that. But yeah, so what are the cases when planes have no intersection? So this is the case when the plane of your table, the plane of the floor, and the plane of any of the walls, they are not going to have any intersection. Okay, no intersection basically. So you could have other similar cases. So you could consider the ceiling now. Okay, so the ceiling above is parallel to both the floor as well as the wall. So if you imagine the ceiling, so the ceiling, floor, and the table, they are all going to be parallel to each other. So this is the case where you have three planes which are parallel to each other. So again, you have no intersection. Okay. Now I want to imagine the case of infinite intersections. So for infinite intersections, consider this wall one, consider wall two, and consider some protrusion which is coming out of this corner of the room, right? So some flap which you have attached to the corner of the room. So these three planes, this plane, the two walls, they will have this entire perpendicular line as the set of intersection points, right? So if you imagine an open book, if you imagine an open book, all the planes, that is all the pages of the book, they are all hinged to one axis. So this axis, the entire axis of the book, it becomes the set of intersection points of these planes, right? And then if you want to imagine the case of a unique intersection, so for unique intersection, imagine these two walls and the floor. So now the intersection point is this single intersection point. Okay, so these are different cases in which you can have either no intersection, you could have infinite intersection, or you could have a single intersection. So this is what this graph tries to explain, that you can have any of these three situations. Okay, coming back to planes and lines. So what I'm basically representing this as generic term as lines. But the idea is that in 3 dimension, we have a distinguishment between lines and planes. So anything of the format uh, alpha x plus beta y plus gamma z equals to 0 equals to c, basically, this will represent a line, sorry, a plane. Okay, and alpha x minus c1 equals to beta y minus c2 equals to gamma y. This will represent a line. So you have lines in 3 dimensions. So this is going to represent the equation of a line, and this is going to represent the equation of a plane. Actually, I should have written this as C1 and C2 here, because it's possible that the lines are not all passing through the origin. Anyway, so what is the distinct feature of a plane and a line? So a line in coordinate geometry is a one-dimensional object in any n-dimensional vector space. In any vector space, the one-dimensional object is called a line, and a plane is basically the two-dimensional object. Right? So in 3 dimensions, a plane looks like this. The equation of a plane would look like this, and the equation of a line would look like this. I'll just be back. There's somebody at the door. Okay, so yeah, so when we have equations of this format, we are basically looking for intersection of planes. So I should not have been calling them as lines. It's the wrong word, because actually these are planes. But in any case, the important thing is there are certain objects in n-dimensional space, and we are trying to find where they intersect. When we are talking about objects in 3 dimensions, these objects are called planes. When we are talking about 2 dimensions, these objects become lines. The important thing is not that whether it is planes or whether it's lines, because clearly our aim is not here to do entire coordinate geometry, and we just want to find how to solve these system of equations. So that is the coordinate angle. Now let's look at the angle for vectors. So the angle for vectors is, let's say I have 3 vectors. So suppose I write that so suppose it looks something like this. Okay, so these are your vectors v1, v2, and v3. So I want to find some linear combination of v1, v2, v3 in order to reach some point b, right? So it is possible that your 2 vectors, the 3 vectors that you are looking at, they all 3 lie in the same place. So suppose my vector v1 is 1, 0, 0. Vector v2 is 2, 0, 0. and vector v3 is 0, 1, 0. Right? So in my XYZ plane, so this is my X, this is my Y, and this is my Z. So in the XYZ plane, vector v1 will be this one, vector v2 will be this one, and vector v3 would be this one. So these three vectors, they all lie in the horizontal XY plane. Now suppose I want to reach some vector as a linear combination of these three vectors. I want to reach the vector b, which is 0, 0. Now, no matter what multiple I take for these three vectors, right, the z component of all these vectors is 0. So no matter what multiple I take for these vectors, it will always end up being 0. So these three vectors v1, v2, v3, I take any linear combination of, I would never be able to reach b. So anything of the format x times v1 plus y times v2 plus z times v3 equals to 0, 0, 1 here would yield no solution. Okay. On the other hand, suppose my b vector was 6, 0, 0. So then I can either take b equals to 6 times v1 plus 0 times v2 plus 0 times v3, right? Because this v1 I take 6 times, so this becomes 6, 0, 0. The rest of them I don't require. Or I can take it as 0 times v1 plus 3 times v2 plus 0 times v3. So I'm taking thrice of this. I don't require this or this. Or you could take any other combinations of v1 and v2. In theory, you can take infinite combinations of v1 and v2. You can take any values of x and y here, as long as x plus 2y is equals to 6 and z equals to 0. So all x, y, and z which satisfy this equations can be a valid solutions. X plus 2y equals to 6. Right, so either you take x equals to, you can even go in negative. X and y can also be negative, by the way. You don't need to be positive. So you can take x equals to -2 and y equals to 4 and z equals to 0. So -2, 4, 0, that becomes another solution. So you can have infinite solutions here. Right, so in such a situation, you would have infinite solutions. So really what I'm trying to say is that there are three distinguishable cases. One obvious case is when you have a unique solution, but these are the two other types of cases when you have no solution or when you have infinite solutions. So the no solution and the infinity of solutions together are called the singular cases. And when you have a unique solution, that is when you call it as a non-singular case. So unique solution implies non-singular. So that's the demarcation. Now, why am I clubbing the no solution and infinity of solutions? This will become clear in some more time. Maybe by the next lecture, we'll be able to highlight why we are taking no and infinite solution as one case and unique solution as a separate case. Okay, so that will depend on the nature of the matrix. Now let us look at, suppose I have this unique solution case. Suppose I have a situation where I am getting a unique solution. So how do I find the unique solution? Okay, so in the subsequent chapter, we are going to look at how to distinguish between the singular and non-singular cases. Right now, I'm going to assume that the case that I have given is non-singular and you have to find the solutions. So this is some system of equations, right? So how do I proceed to solve it? So I'm going to use something which is known as a Gaussian elimination, right? So here I have here I have mentioned how you could do it. Suppose if you do not know any linear algebra, then how could you do it? So one way would be to add equations in such a way to get rid of some of the variables. So remember the simple equation 2x minus y equals to 1 and x plus y equals to 5. The first thing we did was we added the two equations to get this equation 3x equals to 6. So what you did was we added the two equations to get rid of y. We added it in 1:1 format so that y gets eliminated. So the procedure is going to be similar. We are going to add these three equations in a manner so as to eliminate the coefficient for one of the variables, two of the variables really. Once we eliminate two of the variables, the third variable will be found, and then we can back substitute this to get the remaining variables, right? So this is absolutely what we did here, right? So this was 3x equals to 6. Then I back substitute this x equals to 2 in any of the equations, and I get my original values for x and y. So let us now look at how to do this in a shortcut manner. So the way to do this in a shortcut manner would be to use Gaussian elimination. So this was my system of equations. Where's the system of equations? 2u plus v plus w equals to 5. So what I do is I write this in a matrix form. 2. So I'm going to write the coefficients 2, 1, 1, 4, minus 6, 0, minus 2, 7, 2. Okay, and then these coefficients 5, minus 2, 5. Okay. Actually, the way to write this would be u v w equals to 5 minus 2. Now, the way Gaussian elimination works is that you forget about this UVW. Just focus on this matrix of coefficients and this matrix of constants. So, and you write it as a combined matrix. So this is what I've written as this combined matrix. This was a matrix of the coefficients. This is the B matrix. So I've written it as a combined matrix. Okay. Now, we will reduce this left part into something which is called as the echelon form. Now, what is the echelon form? So echelon form is a form which looks like a triangle. So everything below the triangle is going to be 0. Everything below the diagonal of this triangle is going to be 0. Okay, so the echelon form is also known as the triangular form. So I want to reduce this matrix of coefficients into the echelon form. So how do I go about it? So I take this as my pivot entry and I do some row operations in order to make this and this 0. So in order to make this 4, 0, I want to subtract 2 times this to get this 0. So suppose this is my row 2. This is my row 1 and this is my row. So the first step is row 2 goes to row 2 minus 2 times of row 1. So what happens is that this 4 will get subtracted by twice of this. This minus 6 will get subtracted by twice of 1, and this 0 gets subtracted by twice of 1, and this minus 2 gets subtracted by twice of 5. Right? So let me write down, let me copy this matrix from here so that we can work on this. Okay. So I'm going to pivot this entry, and I have to make these things 0. Okay, so just focus on this first column initially. Don't focus anywhere else. Don't look at any other number. Just focus on these numbers. So the question is, how do I make this 0 using this number? So 4 minus 2 times of 2 is equals to 0. So this minus 2 becomes crucial. So what I get is that the entire row 2 should go to row 2 minus 2 times of row 1. Okay, so 4, say you will subtract 2 times of 2, which obviously gives 0 because that's how we came to this minus 2. Then minus 6, say you subtract 2 times of 1, so that becomes minus 8. So let me write down the numbers. The first row remain as it is, 2, 1, 1, 5. The second row becomes 0, then minus 8. Then here you would have 0 minus 2 times of 1, which is basically minus 2. And finally, minus 2 minus 2 times of 5. So that is equal to minus 2. Now, similarly, I want to make this thing 0. So I want to do some operation on row 3 with respect to row 1 to make row 3's leading element 0. So what should be the operation that I do?
R1 plus R3.
Row 3 goes through row 3 plus row 1, right? So that would make this thing 0. So 7 plus 1 is 8, 2 plus 1 is 3, and 9 plus 5 is 14. So this becomes my reduced form of the matrix after doing these two operations. Now remember, I want to make this thing 0 as well. So now what I'll do is I'll make this entry as pivot. Okay, so the pivot entries, they will move in diagonal manner. First you are going to make this pivot, then this pivot, and so on. So for larger dimensions matrices, you are going to proceed in this downward diagonal format. So now I want to do some operation on row 3 with respect to row 2 in order to make this element 0. So what should that operation be?
So row 2 plus row 3.
Very good. So row 3 goes to row 3 plus row 2. All right. So the first row does not change at all because I'm not doing any operations. 2, 1, 1, 5. Second row also I'm not doing any operations. So that remains as it is, minus 2, minus 12. Third row becomes 0, 0. 3 plus minus 2 is minus 1. And 14 plus minus 12 is minus 2. Oh, sorry. 2. And this is also not, right? Row 3 plus row 2. This is 1, this is 2. Okay. So this is the echelon form. This is the echelon or triangular form of the matrix. Now, how do I derive the solutions from this? So now if you expand this back into equations, the last equation is basically 0x plus 0y plus 0 plus 1 times z is equals to b, which implies z must be equal to b. The penultimate equation becomes 0 times x minus 8 times y minus 2 times z is equals to minus 12, in which you can substitute z equals to 2. So what you get is minus 8 times y is equals to minus 12 plus 4, which is basically minus 8, which implies y equals to 4. And the top equation, it becomes 2 times x plus y is 1 plus z is 2 is equals to 5, which implies that x is equals to 1. So once you reach this, after this, it's easy to find my solutions. But another line of thought is that don't stop here, proceed from here. How do I proceed now? Now take this as the pivot. Okay. Remember the last column is the column of the B vectors. Don't do any operation here. Don't make any pivot entries here. Move in this direction, and now you'll see what I'll do. So now what I'm going to do is I'm going to make this pivot, and with respect to this pivot, I'm going to make these entries here. Okay. So now operation will be on row 2 and row 1 with respect to row 3. So first of all, what operation should I do to make this minus 2, 0? In terms of rows, what should be the operation? Row 2 goes
So
to
2R3 plus R2.
2R3 plus R2 or R2 plus twice of R3.
Yes, sir.
Right? So I'm going to add twice of these bottom numbers to the top numbers. So what do the numbers become? So the bottom row remain as it is. So that would be 0, 0, 1. 2. This row, I'm going to add twice of the bottom numbers. So I add twice of 1 here. So this becomes 0. I add twice of 0 to minus 8. I add twice of 0 to 0. It remains 0. Here, I add twice of 2 to minus 12. So that becomes minus 8. Right? And what should be the operation on row 1 with respect to row 3 to make this thing 0?
So R1 is equal to R3 minus R1.
No, R1 minus R3.
Oh, yes.
Okay, so the operation is done on R1. R1 may you add or subtract something on this. So not R3 minus R1, R1 minus R3. So 1 minus 1 is 0. 1 minus 0 is 1. And 2 minus 0 is. And 5 minus 2 is 3. Now as a final step, so I took this one as pivot. Now I'm going to move in the backward direction. So take this as pivot and make this thing 0. So what should be the operation on R1 as something related to R2 in order to make this 1 as 0?
Eight R1 plus R2.
Okay, don't multiply R1 by 8. Rather, R1 plus 1 by 8 R2.
Okay, sir.
Okay. Although what you're saying will also lead to the correct answer, but it's easier to do this. So then the first row becomes 2 plus 1 by 8 times of 0, so that will remain 2. 1 plus 1 by 8 times of minus 8, so that will become 0. This will be 0. 0 minus 8, 0, 0, 0, 1. These numbers, so 3 plus 1 by 8 times of minus 8, so that will be basically 3 minus 1, right? So 3 plus 1 by 8 times of minus 8, so that is 3 minus 1, so that is 2. And then you have minus 8 here and 2. So nothing changes here, right? Now, if you look at the last equation is just 0 times x plus 0 times y plus 1 times z equals to 2, which is basically z equals to 2. The penultimate equation is minus 8 times y equals to minus 8, or y equals to 1. And this top equation is now 2 times x is equals to 2, or x equals to 2. So x1, y1, z2. Now, another line of thought here is that you can even proceed from here. So this is my row 1, this is my row 2, this is my row 3. The next step is, so now that you have eliminated everything apart from the diagonal entries, now do row operations to make these diagonal entries 1. Basically, what I'm saying is row 1 goes to row 1 by 2. So that will make this thing as 1. Row 2 goes to row 2 divided by minus 8. So that will make this thing as 1. And row 3 is already already 1. So leave it as. So when you do that, this entire row gets divided by 2. Okay, when I divide the entire row by 2, all the numbers get divided by 2. So the entire row becomes 1, 0, 0, 1. Then I divide this entire row by minus 8. So this entire row becomes 0, 1, 0, 1. And for this entire row, I'm doing nothing. So 0, 0, 1. So once you reach this format, where you have made this entire thing as the identity matrix, okay, so this matrix is called identity matrix. The diagonal entries are 1, everything else is 0. So these are called identity matrices. So once you have used your Gaussian elimination, so this sort of method is called Gaussian elimination when you keep doing row operations. So when you have done a sizable number of Gaussian eliminations to reach identity matrix on the left hand side, you directly get the result on the right hand side. X, Y, Z, 1, 1, and so this is how you can solve this particular thing. Let me open up one of these examples. Let us see if there are any examples in 3 variables. No, there are not. So this is going to be our homework. So let's look at this first example. Minus 3x1 plus 3x3. Let me copy this. Okay, so when you are solving a complicated system of linear equations, first thing is always write the correct matrix. Okay, so the correct matrix here is going to be minus 3, 0, 3, 0, minus 3. The second equation is minus 1, 2, 0, 2, minus 8. The third equation is 0, minus 2, 2, minus 2, 8. The fourth equation is 2, 4, minus 2, 2. So I know that there are some elements missing. So when there's element missing, so there is no element x2 here. It means that it is 0 times x2. So I have to write a 0 instead of in place of the coefficient for x2 here. So this is how my matrix would work. Now suppose I have to solve this system of equations. Now there's some simplification which you can do. You see this entire row is multiples of 3. So you can divide the entire row by 3. So row 1 goes to row 1 by 3. Similarly, this entire row is divisible by 2. So row 2 goes to row 2 by 2. And this entire row is also divisible by 2. So row 3 also goes to row 3 by 2. So I can do this simple.
Sir, row 3 and row 4 होगा ना?
Oh, sorry, yeah. Row 3 and row 4. Row 3 and row 4. So you can divide this entire thing by 3. So what I'll get is minus 1, 0, 1, 0, minus 1, minus 1, 2, 0, 2, minus 8, 0, minus 1, 1, minus 1, 4, and 1, 2, minus 1, 1, 0. Now I can apply my row operations. So I will pivot this thing, make this thing 0. So row 2 goes to row 2 plus row 1. Row 3 may you don't need to do anything because this is already 0. And row 4 goes to row 4 minus plus row 1. This has to be minus, row 2 minus row 1. And this is row 4 plus row 1. So when I do that, I'll get the matrix. The first row remains as it is, minus 1, 0, 1, 0, minus 1. The second row, I'll subtract the numbers above them. So minus 1 minus minus 1. Okay, so that is 0. 2 minus 0, so that's 2. 0 minus 1, so that's minus 1. 2 minus 0, so that's again 2. And this is minus 8 minus minus 1, so that will become minus 7. Third row remains as it is because you have not done any operation here. And fourth row, you are going to add these numbers. So 1 plus minus 1, 0. 2 plus 0 is 2. Minus 1 plus 1 is 0. And 1 plus 0 is 1. And 0 plus minus 1 is minus 1. Right. So now pivot this entry and make these two values 0. Do the row operations and give me the reduced matrix. Do it in your books.
सर
Yeah.
सर आर रो 3 में सर कौन सा ऑपरेशन लगाया सर? रो 4
So
वाला
to
समझ आ
make
गया.
this 0, row 3 goes to row 3 plus half of row.
अच्छा सर 2 रो 3 प्लस R2 नहीं हो सकता कभी भी कैलकुलेशन में?
कर सकते हो. You
ओके.
can do that. You can do that. The important thing is to make this 0.
ओके सर.
Okay, so you can do that. No problem. But remember, when you do that, first make the entire row twice. पूरी रो को 2 से मल्टीप्लाई करो. These numbers also. And then you subtract whatever you want to do. So if you are comfortable with that, what you'll get in the end is, uh, yeah, maybe you'll get 1 and 1 here,
यस
right?
सर.
Yeah, yeah. So you'll get 1 and 1 here. So what I'm doing is R3 plus half row 2. What you are doing is twice R3 plus R2. So whatever you get is going to be twice of whatever I've got. So iska double mil jayega. So that's okay, no problem. Just remember, multiply the entire row by 2 first, and then you do whatever operation you want to do.
ओके सर.
So if we do that, then we'll get these values. Okay. Has everybody reached this point? Is there anybody who's still working this out? Do I need to wait for anyone? Okay. Finally, we are going to pivot this entry and make this 0. But actually, you don't need to do it, really speaking. I mean, you can even solve from here. You can start from this equation, right? Because one of the equations can now yield you the result directly. So you can start from this. This equation will directly give you x3 equals to 1. Okay, because if you expand this, this becomes 0x1 plus 0x2 plus 1 times x3 plus 0x4 equals to 1. Right? So you can just write x3 equals to 1. Then you look at this equation. So this equation is x3 minus x4 equals to 6, where x3 is 1. So this implies x4 equals to minus 5. Right? Now you put it back in this equation. So what you get is 2 times x2 minus x3 plus 2 times of x4 equals to minus 7. Now you can substitute x3 equals to 1 and x4 equals to minus 5. So what you get is twice x2 is equals to minus 7 plus 10 plus 1. So that is 4. So x2 becomes equal to minus 5. X2 becomes equal to 2. Right? And finally, you can solve this equation that minus of x1 plus x3 equals to minus 1. X3 was what? 1. So x1 becomes equal to 2. So these are your solutions. You don't need to go beyond this unnecessary or ज़्यादा calculations करने का, multiple row operations करने का. I don't see the point. But whatever you're comfortable with. Obviously, the answer given here is wrong. Like a bunch of these answers are wrong. I'll update them. Don't go by these answers. I should have updated them. I don't know why they are wrong. I have solved them, obviously. Maybe I did a mistake there, or maybe I did a mistake right now. So I don't know. I'll have to recheck the answers again. I'll do that. But that is going to be your homework for today. Okay, so that's your homework for today. These problems. Let me just be back. Sorry. All right. So you have to do these problems. So that's your homework. Problem set 1. It's in linear algebra problem set. So in the linear algebra folder, you can go into problem sets. You'll find these problems. Let me come back to the notes. So yeah, so this is basically how you have to do these row operations. Now, sometimes what happens is that when you do the first row operation, so suppose your matrix looks like this: 1 1 1 2 2 5 4 6 8. 1 1 1 2 2 5 4 6 8. Okay, so so 1 1 1 B1, 2 2 5 B2, and 4 6 8 B3. I don't care what this B1, B2, B3 are right now. I'm giving you some other lesson. Okay, so these constants, these coefficients, yeah, so sorry, these B values, the constants, they are immaterial for what I'm going to tell you right now. So that's why I'm not giving these values. So the important lesson is, suppose I do the first row operation. Okay, so what are going to be the row operations if I pivot this and make these zeros? Yuvakshi, why don't you tell me what is going to be the row operation on row 2?
So R2 minus 2 times R1.
Very good. And
R3,
yeah,
R3 will be R3 minus 4 times R1.
okay, fine. So once you do these row operations, what are going to be these numbers? Dhruv, forget B1, B2, B3. Whatever happens to B1, B2, B3, I'm not interested, Dhruv. Just tell me what happens to these numbers.
The bottom row, right?
Yeah, take your time, no problem.
It will become 0, 2, and 4.
Which ones?
The bottom row.
Okay, bottom row, 0 to 4. And what about
And
this row?
the second row, it will become 0, 0, and 3.
Okay, perfect. So now after I do this, the second step was to make this thing as my next pivot and make everything below it 0. But now this pivot itself has become 0. So no matter what multiple I take of this 0, I can never make this thing 0. So what I do in this case is, suppose these numbers are b1 prime, b2 prime, and b3 prime. After doing the row operations, these write numbers b1 prime, b2 prime, b3 prime. So what I do now is I'm going to do a row exchange. Row 2 and row 3 are going to exchange each other. So this becomes 1, 1, 1, b1 prime, 0, 2, 4, b3 prime, 0, 0, 3, b2 prime. So in certain situations, you might end up in situations where this entry, which was supposed to be a pivot, becomes 0, but something below it is not 0. All right. So in that case, you can do this row exchange. And then you can proceed. Okay. So basically, once you do this row exchange, you have seen that everything, this has become the echelon form now. This has become the triangular form. So you don't need to proceed any further. Right. Now, suppose that this 6 was instead 4. 4, 4, 8. So this thing would also become 0. All right. So now what happens is that these two things better be same. Okay. So this thing should be 2 to 4 and 2 to 6. No, wait. 2 to 5. No, let it be whatever this is. Yeah. So now once you reach this format, the third equation becomes 4 times z equals to b3 prime. And the second equation becomes 3 times z equals to b2 prime. So for this to have, so I'm assuming right now that the equations have a unique solution. So for these two equations to give me a unique solution, I should have b3 prime by 4 should be equal to b2 prime by 3. So this should be the relationship between b2 prime, b3 prime. Okay. So because I'm assuming that these system of equations have a solution, we'll definitely do a lot of algebra where the system of equations don't have a unique solution. Okay, so we'll look at those cases separately. Right now, I'm assuming that they have solution. The problem sets that you are going to do, they all have solutions. So we are not going to go into the situations where you have multiple or no solutions right now. We all have unique solutions. So in this case, your b2 prime and b3 prime will follow this relationship and you'll get a unique solution. All set. Okay. The important thing is, even if this happens, the echelon form is reached, right? The echelon form does not say that all these numbers need to be non-zero. The echelon form says that these numbers need to be 0. It is silent on what happens above the triangle. Okay, the triangular part itself, it says you can have zeros or you can have non-zeros. The important thing is that below the diagonal, you should have all zeros. So that is the echelon form. So once you reach the echelon form, you are good to work with the system of equations. Okay, so let's leave at this today.